Yeah, so ladies and gentlemen, it's my great pleasure today to introduce Nastya Molchanova from the University of Vienna. So Nastya has never spoken here. This is the first time for her. So Nastya got her PhD in Novosibirsk 2016, and then she spent 3 years in Russia, and mostly at the Novosibirsk University as assistant professor and so on. And then she moved to the University of Vienna to the group of Ulisa Stefanelli in 2019. She has been awarded a couple of grants, like particularly Lisa Meitner Fellowship, and now she's holding a REVIRE grant, which stands for Reinforced Women in Science. Reinforced Women in Science, and her expertise is in the calculus of variations, quasi-conformal math, and say functional analysis. And calculus of variations applies to material science, and I think from this topic is also today's talk.
Thank you very much for the introduction. I have to correct you. I was first in a group of Elisa Daven.
Okay.
And then in a group of Lisa, it's not that important. So I would like to present on this seminar something more about elasticity and what we did with Elisa and Lisa. And so, as you can see, the title is the variational model for hyperelastic capacitors. Let's see what it is. So, first thing is I would like to mention here is electrostatics, something from what you probably remember from high school. We have a capacitor, 2 plates, one with positive charge, another with negative, and a capacitance is an ability to store energy, electrostatic energy inside of this thing. Here we take V as a potential.
I'm sorry, you have to share the screen.
It's not shared. Let's see.
Where is the zoom here?
Share screen.
Share screen. But where is your screen now? This one.
Was there someone complaining?
Yeah, someone was.
Oh, someone was watching.
Then maybe Control L. Could you Control L to make it large? The full screen.
Oh, good. Yes. Okay, so no, wait, no, that's not how it works. Can we get rid of this stuff?
Yeah, just make it nice.
But we have the. Okay, can I get rid of also this panel?
Yeah, so no more height loading.
Let's see. Let's see this. Okay, as you can see here, Q is a total charge with electric potential, and E here is electric field. Then technology. Then the electrostatic capacity is given with this formula. Actually, from the books of physics, you see some different formula with risk potential, but this is the same. And this is a formula I like to work with. Well, let's see. Another part, so it was hyperelastic capacitor. So what capacitor we just discussed, what hyperelastic means, I'm sure everyone on this seminar knows it very well, but I'm just shortly remind you. We have a physical body, material body occupied domain omega. It's a reference configuration, Then we consider some deformation, a map from RD to RD, and the deformed configuration is wire-formed. Then elastic energy, in case of hyperelasticity, is given by this formula. So this E is not the same as was on the previous slide, but anyhow, so we have W and stored energy function, and the energy is given by in this integral form. So when we speak about charged elastic materials, what do I mean under this? Again, we have our reference configuration, our deformed configuration. For this problem, what we do, we fix part of the boundary, so we consider the boundary conditions on something, some part, maybe everything, maybe a part of it. And inside our elastic body, we have something else that can be charged. So basically, we have a charged elastic thing, and around it some insulator. So the yellow omega is not charged, and orange omega can be charged. And now what we have here is an energy of this form. So you can see the elastic part, integral of W, and a part given by electrostatic capacitance. So the idea behind is motivated by core shell polymers, when you can have a core that you can charge with some changing pH of water around, and shell cannot be charged, it's insulator, and you have here a competition between some elastic behavior and capacitor behavior, electrostatic behavior, because let's say the orange thing wants to be as close to a boundary of big omega as it can be, but there we have some elastic layer, so it cannot go too much to the boundary. Yes, that's what I said. So we have elastic energy and electrostatic energy, and they kind of compete into each other. So we are interested in existence of minimizers of such energy. So if such a body can be in equilibrium. Well, when I'm discussing minimizers of energy, of course, I need to say what is a set of admissible deformations here. And here, my set of admissible deformations are homeomorphisms. Why so? Because I want to consider my deformation to be very good. So it doesn't break, it doesn't create some material, some material doesn't disappear with no reason, and that's why I'm taking homeomorphisms as a admissible deformation. So yes, you could see here a functional G that was known before, but the functional G is given in this way. So as I said, we have our energy, again elastic and electrostatic, and we have a class of admissible deformations. So directly in a functional, we encode that it's a Sobolev function and it has the boundary condition. Well, of course, we need to ask something from our elastic energy, so that we don't have much problems with elastic part. And we asked the standard conditions that W is frame indifferent, polyconvex, and satisfy some certain coercivity conditions. You can see here our favorite positive determinant saying that it doesn't change orientation. And basically, those conditions are given in a way that we don't have to worry too much about elastic behavior, because in this work, we wanted to concentrate on electrostatic behavior. So that I just moved what was before here on the slide. How would we prove existence of minimizers? Let's say we take a minimizer sequence, which exists because if we insert identity map into our energy, it is finite. And then, using recursivity, we get that our sequence is weakly convergent in Sobolev space. We would like to see that the limit y is a homeomorphism, because we want it to be an admissible deformation. And we need to check that our energy is lower than continuous. Well, let's see. What can we say about admissible deformations? So let's say we have a deformation y, which is admissible. Then it has the following properties. So it has a finite distortion. So this KYD, it is a distortion coefficient, which let me write it here then. So dy power d, ouch. So that is KYD, and I'm saying that it belongs to a ds, means integral. But this is exactly a term that we have.
The power in the denominator, the dy is the power of the definition, because in the denominator.
No, well, so I move this the
Yeah, but also above.
no, if I move the distortion that maybe you used to, is this one in a power? Just some notations. Well, this term we have exactly in energy. So we have that this equivalent of the light. Thank you. So what we have that distortion is integrable in a nice power. We have that our deformation doesn't change orientation. From this condition, the second condition, one which I didn't write on my slides, we have S bigger than dimension -1. And so using quasi-conformal analysis, we know that such map, so a map with finite distortion, which distortion is integral in power S, which is bigger than d-1, we have that this map is continuous, open and discrete, or constant. But since we have a fixed boundary condition, it cannot be constant, so it's continuous, open and discrete. And as well, we have property that y satisfies using n and using n-1 conditions, meaning that sets of measure 0 are mapped to sets of measure 0, and preimages of sets of measure 0 are half measure 0. So everything that I mentioned are good for being an elastic deformation. Moreover, if we know that our admissible, or whatever, y is a weak limit of W1Q homeomorphisms, then this y is injective almost everywhere, and together with openness and discreteness, we may say that it's a homeomorphism. So just let me take the essence of all those properties that we wanted, that we need for our for this topic. So we have a y that has finite energy. Then we know that it doesn't change orientation, so determinant of dy is because of 0. We know that it is continuous, open, and discrete. And if it's a limit of homeomorphism, that is a homeomorphism. which means that if we have a minimizing sequence, yn, that converts nuclei to y, then the limit y is also admissible for our function. This is a part of compactness. So let's say if we have a minimizing sequence, we have a limit, and limit is also admissible information. Not a rocket science here. Now let's see the most interesting part of this work, which is a lower semi-continuity of, that is not most interesting, that is a standard. Yeah, so here, so for elastic part is semi-continuous. It's standard, okay, maybe it's what is not super standard is see that low semi-continuous of this distortion part, but it's also kind of classical, so there is not much to do. And yes, now it's the most interesting part, that is me. It's to see the lower semi-continuity of electrostatic part. So again, what we have our minimizing sequence. We have with limit in Sobolev space, and this is what we want to see. We want to see that 1 over capacity is less or equal than the inf of 1 over capacity of our sequence. Let's discuss some properties of capacity. Again, this is a picture. Here we have an open set D, which is y of omega in our setting, and some set inside. Capacity, let me remind you, is given by this integral form. So it's a Dirichlet integral, and admissible functions for capacity. So here V is a potential. So the admissible potentials, let's say it's functions W1 or H10, which are 1 or bigger or equal than 1 on some given set E. Yeah, roughly speaking, you have 1 here, you have 0 somewhere outside. So, and you are searching for potential between these two sets. What can we say about capacity? So those are some basic monotonicity properties of capacities. Most of them follow directly from definition, like this one. So the smaller core set you have, the smaller capacities. Another property compares the outer set, D. Then we know some properties like this. Yeah, so it's kind of approximation of set from inside, from outside, and what can we say about continuity properties of capacity here. So now, having the properties that you cannot see anymore, we can prove that capacity, the one that I defined here, is upper semi-continuous. Well, what do we have here? We have again our sequence of homeomorphisms that converge uniformly in the full domain boundary. This is a picture. So we have the orange small omega is mapped to a mouse, and the yellow big omega is mapped to a cat. And here is something what approximating sequence does. Here you don't really see that it's a cat and a mouse, but you know the bigger ends and what you go to what you want. And then we have upper semi-continuity of sequence. Why upper semi-continuity? Because we want a lower semi-continuity of 1 over capacity. So basically, that's what we want to put here. So let me discuss a little bit the proof. So again, you can see here yellow and orange our default configuration of a limit, and some green and purple for yn for approximating sequence. So what do we do here? We want to estimate this limit. So the thing that we do, actually, we need to find some domain. So two domains that are kind of good, which are so the bigger one should be inside both yn omega and y omega, and for the small one it should contain both y small omega and yn small omega. And then we have this inequality by properties of capacity I was showing you before, and then we send basically we take these two infima separately. Again, by those approximation properties of capacity, and we get what we want. Of course, I'm telling it like this, but there are some technicalities inside that you need to work with, and but this is basically the essence of the proof. And let me summarize here. So we have a functional for which we want to find to prove the existence of minimizers. So we do some tricks with upper limit and lower limit to get a lower semi-continuity of the full energy here, as we wanted. And now, using a direct method of calculus of variations, we want to. So what do we have? We have that since infimum of our energy is finite, there exists a sequence, the minimizing sequence that we have. The minimizing sequence converge in solid space that we also have. And then we need to see that limit is an admissible deformations that we discussed already, and lower semi-continuity of energy, and that we also have. So we are happy. But here I come to a point where I have to admit that I was not entirely honest with you, because the statement I provided you before is not really correct, since we need to ask some regularity of the deformed configuration to do this business with approximating sets of y omega and yn of omega. In particular, this is the correct statement. And here you see, so basically this yellow thing is a difference from what I presented you before. Here, one space W12 0 is a space of just a closure of C0 infinity in Sobolev norm, and the other space, again W120, is a space which is taken from functions, Sobolev functions defined in all Rd, which are 0 outside of set. And these two sets, well, okay, so the point is that this is a technical condition. We need to prove upper semi-continuity. I don't have any counterexample to say that if this is not true, then upper semi-continuity doesn't hold. But I cannot prove without this condition. So in particular, let me bring you some examples when it is like this. And so what do we have here? If our domain, all our domains have C0 boundary. Good, but yeah, you may know that even a homeomorphism can give you a very ugly boundary. Let's say a Koch snowflake in 2 dimensions doesn't have C0 boundary. C0 meaning that it's locally a graph of C0 function. Another option is to say that all our yn have uniformly Lipschitz boundary, which is very strong condition, or you may ask some other conditions of regularity. Of course, they have to be uniform because we want to pass to the limit. And for example, it can be this one that is written in a very small letter, so no one can read it. Let's say some cone condition is fine here. And there are some research that I mentioned in our paper. You can check it later on if you want, where you can actually describe this regularity in the terms of map yn. So you don't ask directly regularity of yn of omega, but you ask something for the function yn, some particular conditions that will tell you that your boundary is regular enough for doing this business. And here I think I'm done, and since it's December, I think it's time for some Christmas pictures.